Hi friends, welcome back. In the previous session, we have completed Fourier transform. So continuation for the Fourier transform, next thing what we have to discuss is sampling theorem or sampling process. So here, why sampling? What is the need of sampling if somebody is asking? Then the answer is, it can convert a continuous time signal into a discrete time signal. The process of converting a continuous time signal into discrete time signal is called as sampling. First of all, you may get doubt why we have to convert a continuous time signal into discrete time signal. What is the necessary for it? Then we can say this is the advantage or this is the application which we are using in the A to D converter. That means analog to digital converter. So in the analog to digital converter, the intermediate process is nothing but the sampling. So try to understand this one. Suppose, let's say, if I ask what is a sampling? It is the process by which a continuous time signal is converted into discrete time signal. Discrete time signal. So what is the application of the sampling? Actually, that is in the A to D converter. So ADC, A to D converter, okay, or A to D converter. Analog to digital converter. Suppose, let's say, what is this analog to digital converter and where we are using the sampling? So if I say what is the block diagram for A to D converter, then the first thing what we got is nothing but sampling. This is the sampling. First block has to be sampling. Next, once the sampling is done, then we are having quantizer. Next, once it is quantized, then we are having encoder. Encoder. So this is the block diagram for A to D converter. So for this A to D converter, if the input is a analog signal, analog, then the output is a digital signal. Digital signal. So the intermediate step, the first step, what we have to do is nothing but the sampling. Suppose if somebody is asking what is the output of this signal, this is nothing but discrete time analog signal. Discrete time analog signal. So what is here? It is a continuous time analog signal. Continuous time analog signal that can be converted into discrete time analog signal. Then this is going to be quantizer. What the quantizer will do? That will quantize the values of the amplitudes. That means, suppose if we are having 2.3 is the amplitude at particular value of n, then that can be converted into 2 or 3 or something like that. So it is going to be quantized. Then that is going to be called as discrete time digital signal. Discrete time digital signal. Once we quantize it, then that is going to be encoded like a zeros and one. So then what is going to be? So for a certain duration we are going to get 1, for a certain duration we are going to get 0. So then it is going to be a continuous time signal only, but it is having the amplitudes only 0 and 1. So I can say it is nothing but a continuous time digital signal. A continuous time digital signal. So to convert a continuous time analog signal into continuous time digital signal, the intermediate process is called as sampling. So this sampling what we are talking about now. So this is the sampling process what we are interested in. This is the sampling process what we are interested in. So we are having various sampling process. So types. Let's see what are the types of samplings. In that one, the first one is ideal sampling. Second one, natural sampling. Third one, flat top sampling. But in our syllabus, we are having only ideal sampling. So this is the only thing we are having in the syllabus. Ideal sampling. So we don't have to worry about natural sampling or flat top sampling. So this is the only thing we are going to see now. Okay, take it. Converted into discrete time signal. Let's see. Ideal sampling. So let's say we are having a continuous time signal x of t. A continuous time signal x of t, which is shown like this. Let's say. Now let's say it is having Fourier transform x of omega. I don't know what is that x of omega for the time being, just I am doing this one. So here the signal what we have is a continuous time signal. Continuous time signal. If this signal is multiplied with a impulse train, one at Ts, at 2 Ts, minus Ts, and so on. So this is called as P of t, P of t, which is called as impulse train. Impulse train. If I multiply these two signals, then the resultant signal is called as xs of t, that is sampled signal, which is nothing but x of t multiplied with p of t. X of t multiplied with p of t. Then how it is going to look like? Xs of t. So we are not going to get a continuous time signal. So instead of that, because the impulses are existing only at 0 Ts and 2 Ts seconds, then we are having impulses only at 0 Ts, 2 Ts, minus Ts, and so on and so on. So here the signal what we got is nothing but sampled signal. Sampled signal. And if you observe, this is nothing but a discrete time signal. Discrete time signal. So this is the simple ideal sampling. So what is ideal sampling? So the given signal is multiplied with impulse train with a period Ts, and this Ts is called as a sampling period. This TS is called as sampling period. So if I multiply them, then we are going to get a sampled signal, which is nothing but a discrete time signal. So let's analyze the same thing in the frequency domain. So let's call the impulse train is having Fourier transform P of omega. Then what is the Fourier transform for sampled signal? So what is P of omega actually? 2 pi by Ts. So actually Cn value is nothing but area by period, that is nothing but 1 by Ts summation m is equal to, let's say, n is equal to minus infinity to infinity delta omega minus n omega s. What is omega s? 2 pi by Ts. 2 pi by Ts. Then what is the Fourier transform for sampled signal excess of omega? What is the Fourier transform for this signal? And yesterday, so in the previous session, we have seen multiplication in time domain leads to convolution in the frequency domain, but with the factor 1 by 2 pi. So I can say this is nothing but 1 by 2 pi x of omega convolution with P of omega. Convolution with P of omega. So what is this? Let's say 1 by 2 pi convolution. So I can write 2 pi by Ts. 2 pi by Ts x of omega convolution with summation n is equal to minus infinity to infinity delta omega minus n omega s. Because convolution is a linearity property, I can take this convolution inside the summation. Then so first 2 pi get cancelled, 1 by Ts summation n is equal to minus infinity to infinity x of omega convolution with delta omega minus n omega s. And we know any signal is convoluted with impulse, we are going to get the same, but we are having the shift, so we have to introduce the same shift. So I can say summation, sorry, first 1 by Ts 1 by Ts summation n is equal to minus infinity to infinity x of omega minus n omega s. Omega minus n omega s. So this is what excess of omega, that means Fourier transform for sampled signal. So what is this Fourier transform, how we can represent these things? We will see that. First you can take this one. Okay, take it. E having x of omega, let x of omega is shown like this. Zero omega m minus omega m 1. So I can say about the signal x of omega, it is having maximum frequency which is omega m. What is the minimum frequency? 0. So 0 to omega m, the signal is existing from 0 to omega m. So I can call this signal as a low pass signal or baseband signal, because it is existed in the base of frequencies, or we can say low frequencies. So I can say it is a baseband signal or low pass signal, and it is a band limited signal also. Why it is called as a band limited signal? Here the bandwidth of the signal is a finite value, so that is nothing but omega m minus 0. So I can say it is a band limited signal. So I can call this is baseband signal, baseband signal, or we can say, and not or, and it is also called as a band limited signal. band limited signal. And remember, sampling theorem is applicable only for band limited signals. So I am writing that point. So very important note. Sampling theorem is applicable only for band limited signals. That means the bandwidth must be finite. That is, bandwidth is equal to finite. Then only we can call it as a band limited signal. And remember, sampling theorem is applicable only for band limited signals. Only for band limited signals. Next, x of t multiplied with p of t. This is called as xs of t, sampled signal in time domain. So for this, we got xs of omega is equal to 1 by ts summation n is equal to minus infinity to infinity x of omega minus n omega s, x of omega minus n omega s. So if I expand this one, so this is going to be, and so on, 1 by ts. Suppose n value is equal to minus 1, then this is x of omega plus omega s, plus if n value is equal to 0, then 1 by ts x of omega. If n value is equal to 1, then it is going to be 1 by ts x of omega minus n omega s, plus and so on. So this is the expansion. So what do you mean by that? Every spectrum, that is x of omega, this is a shifted spectrum to the right side, this is a shifted spectrum to the left side. So every spectrum is multiplied with 1 by ts. That means, so here we are having 1 here, so then we have to multiply with 1 by ts, so it is going to be 1 by ts, and x of omega is there, and it is shifted to right side by omega s. After that 2 omega s, 3 omega s, or if it is shifted to left side, omega minus omega s, minus 2 omega s, like that it is going to go. So keep on, it will go. So here some of the terms we are having. First thing is, what is ts? What is ts? ts is nothing but sampling period. Sampling period. So what is the unit for this? Seconds. Seconds. Next, what is omega s? Omega s is nothing but 2 pi by ts. 2 pi by ts. Here this is a sampling frequency. So sampling frequency. What is the unit? Radians per second. Radians per second. So we are having fs also, absolute frequency. That is nothing but simply 1 by ts. So this is also called as sampling frequency or sampling rate. Sampling rate. What is the unit for this? Sometimes it is hertz or samples per second. Samples per second. So these are the terminologies you have to remember. So depending on omega s value, that means sampling frequency, we can divide the sampling into 3 types. One is oversampling, critically sampled, and another one is undersampling. So we will see one by one. What if it is more? What if it is less? What if it is equal? Then we will see one by one. First, take down this. Let's see. First one, oversampling. Oversampling. What is oversampling here? The sampling frequency omega s is greater than 2 omega m. 2 omega m. Then we can call it as a oversampling. Let's take a particular example. Let omega s is equal to 3 omega m. So I know how to write excess of omega. So if I write x(s) of omega, wherever omega s is there, replace with 3 omega m, then and so on, 1 by ts x of omega plus 3 omega m plus 1 by ts x of omega plus 1 by ts x of omega minus 3 omega m plus and so on. Like that we can write what is excess of omega. Now I want to represent graphically, that means spectrum. So if I draw the spectrum, let's say how it is going to look like. Xs of omega. So first 1 by ts x of omega, that means the same signal but amplitude is nothing but 1 by ts. So we are going to get like this. Zero omega m minus omega m 1 by ts. Next, x of omega minus 3 omega m with a factor 1 by ts. That means the same thing has to be shifted right side by 3 omega. So if I shifted right side by 3 omega m, then what will happen? Each instant has to be added with 3 omega m. Then this will be added with 3 omega m. So plus 3 omega m. So it is going to be 2 omega m. Then it is going to be 3 omega m. Then it is going to be 4 omega m. So it will look like this. 3 omega m, 2 omega m, 4 omega m, and so on it will go. So if it is shifted left side, so it is also going to be the same. Minus 3 omega m, minus 2 omega m, minus 4 omega m, and so on. So again it will be shifted to 6 omega m, 9 omega m, like that. So it is going to be minus 6 omega m, minus 9 omega m, like that. So but everything having the same amplitude 1 by ts. Okay. Now, so this is what the sampled version. So we are having the original signal x of omega. Then we are having this is a sampled signal. Now you tell me. So I want to get back my original signal x of omega. Then what we have to do? We are having a sampled signal. So from this sampled signal, I have to get back my original signal. So to reconstruct my original signal, what I have to do? I have to pass the signal through a low pass filter with a cutoff frequency is equal to omega m. So if I pass the signal through a low pass filter, then this will be comes out, and these two are after that everything is going to be compressed. Sorry, everything is going to be eliminated. So we are having only this is the one x of omega. So just we are having a less amplitude, but still we can get it back by amplification. So we don't worry about the amplitudes here. So we have to worry about the frequencies here. So to get back my original signal, I can pass this through an ideal low pass filter. Suppose we are having an ideal low pass filter which is like this. This is a ideal low pass filter. Ideal low pass filter. So can I get back my original signal if it is passed through ideal low pass filter? Yes. Or if I ask, is it necessary to use the ideal low pass filter? Can I use a practical low pass filter to get back my original signal? Yes, I can get back my original signal. But I have to maintain a constant value only up to this one. After that, it can decrease. So that means we don't have to get a sharp cutoff characteristics. So even though we are having somewhat this kind of characteristics, still it is going to be possible to get back my original signal. So this is a practical low pass filter. Practical low pass filter. So here we can use the practical low pass filter also to get back my original signal. That means I don't have to go for the ideal low pass filter. Why? Suppose if I ask why it is possible to use the practical low pass filter also. Now observe carefully. So this is the original spectrum and this is the shifted spectrum. If you observe carefully, there is a gap between original spectrum and shifted spectrum. How much is the gap actually? 2 omega m minus omega m. That is nothing but omega m is the gap. That omega m gap or this gap is nothing but called as guard band. So this is called as guard band. Because of this guard band, I can use the practical low pass filter also. If I don't have this guard band, so if I use the practical low pass filter, that will pick up the next version also. That means shifted version of the original signal also. I hope you understood what I'm going to say. See, if I use the practical low pass filter, if I don't have this gap, then I will pick this portion of the curve also. Then what will happen? That is going to be unwanted signal for us. So I don't want that signal. So I want only this signal. So I can use the practical low pass filter because of there is a gap between them. And this gap is called as guard band. So in oversampling, we are going to get a guard band. So how much oversampling you are doing, depending on that, we are going to get the guard band. So if you get a large guard band, so I can get back the original signal with a more practical low pass filter. So I hope you understood. So the gap between original and shifted version is omega m and it is called as guard band. This is called as guard band. So because of the existence of guard band, I can use practical low pass filter also. So what are the key points here? Key points. One is omega s is greater than 2 omega m. Second one, guard band exists. Guard band exists. Next, to recover or to reconstruct the original signal, even practical low pass filter or to get back the original signal, no need of ideal low pass filter. No need of ideal low pass filter. Ideal low pass filter. So these are the key points we have to remember in the oversampling case. Okay, take it. That is a critical sampling. Critical sampling or sometimes called as Nyquist sampling. Nyquist sampling. Nyquist sampling. So here in this one, the frequency is sometimes called as Nyquist frequency. Nyquist frequency is equal to exactly 2 omega m. Exactly equal to 2 omega m. then what will happen? So if it is exactly equal to 2 omega m, then excess of omega will look like this. This is a 2 omega m, 2 omega m, exactly. Then how it is going to look like? Let's see. Excess of omega. So original one, which is existing between if it is shifted right side by 2 omega m, then what will happen? This will be plus 2 omega m. So it is going to be omega m. This is 2 omega m. This is 3 omega. Then the signal, the shifted version will look like this. So this is 2 omega m. This is 3 omega m. After that it will be continuum. So it is keep on repeating. Next, if I see here, and so on like that. So this is the sampled signal. So we are having the shifted version which is exactly starting from omega m. So if I want to get back my signal, that means I want to reconstruct the original signal, then what I have to do? I have to use ideal low pass filter. So there is no way you can use practical low pass filter, because if you use practical low pass filter, that will take the next portion, that means that will take this shifted version also. So I cannot do that. So I have to pass the signal, the sampled signal, through an ideal low pass filter only. This is what? Ideal low pass filter. Ideal low pass filter. Now if I ask, do we have any guard band here? No, we don't have any guard band. That's why we have to use ideal low pass filter. If I have any guard band, I can use the practical low pass filter. So I can say this is the minimum sampling frequency I have to use. So if I go below that one, it is not even possible to reconstruct. So I can say ideal low pass filter is must and should to get back my original signal here. So what are the key points here? First one, omega s is equal to exactly 2 omega m. Next, second one, no guard band. No guard band. Next, third point, to reconstruct original signal, we must use ideal low pass filter. Ideal low pass filter. So I cannot use a practical low pass filter here. I have to use the ideal low pass filter, because there is no guard band. There is no gap between original spectrum and the shifted spectrum. So I have to go for the ideal low pass filter only. Clear? Take it. Third case, under sampling. That means we have to take sampling frequency which is less than 2 omega m, which is less than 2 omega m. Specifically I will take let's say 1.5 omega m, so which is less than 2 omega m. So what if it is going to be 1.5 omega m, then what is excess of omega, how we can represent graphically. So here xs of omega is equal to, and so on, 1 by ts x of omega plus 1.5 omega m plus 1 by ts x of omega plus 1 by ts x of omega minus 1.5 omega m, and so on. It will keep on repeating like that. If I draw this excess of omega spectrum, omega, excess of omega. So first let's say 0 omega m minus omega m. One by ts. Now if it is shifted to 1.5 omega m, then what will happen? I have to add 1.5 omega m, so it is going to be 0.5 omega m. If it is added here 1.5, so it is going to be 1.5 omega m. So if I add 1.5 omega m here, so that is going to be 2.5 omega m. 2.5 omega m. So if I draw this, so this is how it look like. So here also omega. So this is what it is happening here. Suppose if I do undersampling, that means if I take omega s value which is less than 2 omega, then what will happen here? So there is always interference from high frequency signal with low frequency. Why? If you observe carefully, this is what the original signal. So this is the shifted version. So if it is a original signal, we can call it is a baseband signal or low pass signal. Once it is shifted, then it will become high frequency signal, or we can say pass band signal. So what is this high frequency signal is doing actually? So it is interfering with the low frequency signal. So I can call this is interference. This is interference, or sometimes called as aliasing effect. This is called as interference, or aliasing effect. Aliasing. So because of this interference, suppose I want to get back my original signal. So if I pass through even a ideal low pass filter, still because of the interference, I am not going to get back my original signal. I am not going to get back my original signal. So I cannot get back my original signal even if I use ideal low pass filter, because it does not have any guard band, and it is interference, and there is a interference from high frequency signal with a low frequency signal, and it is also called as aliasing. What do you mean by aliasing? You might heard these kind of words in news channels or something. So they will say Ramesh alias some person name, and they will say Maoist or some Naxalite names like aliasing. The word is using aliasing. What do you mean by that? Suppose Ramesh alias Suresh or something like that. Then what you can understand? this person is taking the identity of some other person and behaving like some other person. That's what the meaning of aliasing. So here also the high frequency signal we are having is behaving like a low frequency signal and interfered with low frequency signal. So that is called as aliasing effect. So this high frequency signal taking the identity of the low frequency signal, then we can call that is aliasing effect. So what are the key points here? The key points. The first one, omega s less than 2 omega m. Second one, no guard band. No guard band. Next, third one, interference occurs. And we cannot get back the original signal. Get back the original signal. We cannot get back the original signal. So this is about the aliasing effect. Clear? And one more thing I want to say. What is aliasing effect? High frequency signal is taking the identity of low frequency signal and interfered with low frequency signal. Take it with a low frequency signal.